Uh, this is our first bear talk in the Renormalization group, and uh, I'm delighted to introduce Mr. Niladri Chakraborty, uh, who is a who was a MSc student from IIT Madras, and currently he finished a project at RRI. Uh, I know Niladri from his bachelor's. His main research interests lie broadly on quantum information theory and many-body physics. Uh, and today he will give a talk on chaos, entanglement, nexus in thermalization. So, Niladri.
Hello,
Yes,
am I audible?
yes.
Okay, so yeah, thanks Devajyoti for inviting me. So today I'm going to present my master's thesis, Chaos RMT Entanglement Nexus in Thermalization. So I will mainly discuss about two aspects of many body physics. One is chaos and another one is entanglement measures. So first I will start by summarizing the scientific background. So the first thing is, what is chaos? So chaos is defined by two characteristics. One is a dense set of unstable orbits in a bounded phase space. For example, if we consider a parametrically driven harmonic oscillator or parametrically driven pendulum, what we can see that when we consider the harmonic approximation, we can see some nice periodic orbits. Whereas when we take the nonlinear limit, we do not use the harmonic approximation. We can see that the phase space is dense, full of orbits, which are firstly not periodic, and they are dense. So to be precise, this is not exactly phase space trajectories. This is what is known as stroboscopic map. It is very useful to study driven systems. So So one observation from the plot of forced pendulum, we can see that complete chaos and complete regularity are exceptional. We can see that some of the regions are full of dense, unstable orbits, but still we can get some regular orbits in some regions. Another characteristic is exponential sensitivity to initial condition. So if we deviate for chaotic system, if we change the initial condition slightly, that slight perturbation leads to exponential separation. For example, again, if we take the previous system and we just change the initial condition slightly, with the harmonic approximation, we can't distinguish between the two trajectories with our naked eye. But if we look at the other case where we are not considering the harmonic approximation, we can see that there is a deviation just because of a slight perturbation in the initial condition. So these are the two characteristics of a chaotic system. Now, one important family of Hamiltonians while studying chaotic system that arises is kicked Hamiltonian systems. So it is called kicked because of this delta wave train. So this potential V of Q, it is non-zero only where the delta train is where the delta train has peaks. Now, integrating the Hamilton's equation of motion, we can again get a stroboscopic map that given Q0 and P0, we can just iterate and we can get the time evolution. So one special example is the standard map where we choose the f of p to be simple kinetic energy term and the potential to be a sinusoidal term. And then this standard map, we can, if we plot the stroboscopic map of the standard map, we can see that for this parameter value k, which is arising here. So depending upon the parameter value of k, we can see different property of the phase of the stroboscopic map. So when k is very small, we can see that there are periodic orbits. It is full of periodic orbits. But as k increases, we can see that uh, some of the region is full of periodic orbits, but then there are some unstable orbits. The more we increase the k, we can see that the periodic orbit vanishes and it becomes entirely chaotic. This is just one example of a kicked Hamiltonian system. We will again come back to it at the end of our presentation. Now, why we should study quantum chaos? So, quantum chaos is, I mean, considering the centrality of Hamiltonian systems in physics, quantum chaos is inevitable because we can, if when we are studying 1.5 degree of freedom system, that means one-dimensional systems, which also depend upon time, or some chaotic abstract systems. While quantizing them, we can see quantum chaos. Apart from them, we can also, while studying quantum dots or chaotic scattering or atoms subjected to strong fields,
Hello.
again we see that
Hello,
quantum.
Niladri.
Niladri.
Hello, hello.
Uh, yes. Why are
Yes,
you
why are you
calling?
calling it?
What you
What is
mean by
what you mean by
1.5 dimensional
1.5
system? Can you
dimensional
explain?
system? Can you explain?
Yeah, so 1.5 degree of freedom means so one dimensional systems, but the Hamiltonians are not independent of time. So for one dimensional system, you have the phase space of two dimension. But now, if you consider the time dimension as well, so for two dimensional phase space, you call the system to be one dimensional system, right?
Okay.
Hello.
Yes.
Yeah.
Yes.
So if you consider the time axis, then the phase space, the extended phase space, it becomes three dimensional. So we can call it 1.5 degree of freedom systems.
Okay. Okay. Okay.
Is that fine? Yeah. So apart from them, apart from these things, also it has been shown that even the eigenvalues of quantum chaotic systems, and there is a similarity between zeros of Riemann zeta and the eigenvalues of quantum chaotic systems. And apart from that, also in quantum chromodynamics and also defined spin chains, quantum chaos arises naturally. So I guess this
Similarity
is a
means. Are
motive.
you want to talk about that? The eigenvalues are the Riemann zeta functions. Eigenfunctions are like Riemann zeta functions, something like that, or not,
No,
not
no, no.
that.
I will come to that. What I mean by
Okay. Okay.
zeros of Riemann zeta mimics like eigenvalues of quantum chaotic system. I will come to that. So the first thing is there any quantum chaos? Because in Hilbert space, we cannot get any exponential separation. So if you just look at the time evolution, because of the unitarity of the time evolution, the separation between, the overlap between two initial states, they remain the same in even after the time evolution. So unlike the chaos in phase space, quantum chaos is not defined by some separation in Hilbert space. But still, we can argue that quantum chaos exists because we can draw a connection with the Pero-Frobenius evolution of phase space. So just like wave function is not localized localized. So similarly, in classical mechanics, we have density function, which is also not localized and which is also unitary. Still, in classical systems, we can see chaos. So just because there is no exponential separation in Hilbert space, we cannot claim that quantum chaos does not exist. Quantum chaos is there, but we have to define it differently, not exactly like how we defined in phase space. So one
Niladri,
trick to
in the
do that
previous slide,
is,
I have a question.
yeah,
Yeah.
sure.
This phase space density function that you have defined there, there is a factor of exponential minus t times L. I think, if I am not wrong, that L is Lagrangian.
No,
What is
L
that?
is the Liouvelian operator.
Okay, L. What is that? Uh,
So the L operator is L acting upon rho. It gives you the Poinsot bracket of rho comma h.
okay, okay, okay. So,
So
okay,
this is so if you just integrate the Liouville's equation, you will get this.
I see, I see, I see. Now I understand. Yes, yes. Okay.
Yeah. So one trick to do this is we can define something which is called Wigner-Weil transformation. So Wigner-Weil transformation takes a quantum operator and maps it on the phase space. So using this transformation, if we take the density operator and perform the Wigner-Weil transformation, what we get is known as Wigner function. So this Wigner function serves the purpose of this wave function. I mean, in quantum mechanics, just like we have wave function, in this we can describe this Wigner function as our quasi probability distribution, and then we can see whether there is something like quantum chaos or not. So if we take the semi-classical limit, Berry-Voros hypothesis says that the phase space average of this Wigner function, it goes over to the microcanonical ensemble average of an operator. I mean microcanonical ensemble, and if we do this for an operator, that if we take the limit h bar tends to 0, then the expectation value of an quantum operator using this Wigner function and this Wigner-Will transformation, ultimately what we get, that it is the same as microcanonical ensemble average. So this is what we call as thermalization. We will get into more detail. So this is one approach that we can study the quasi probability distribution. The another approach is studying energy level statistics. So if we take two systems, one which is classically integrable and one is classically non-integrable. So Berry-Tabor conjecture says that if a classical system is integrable, then then for its quantum counterpart, if we if we plot the histogram of the separation of the eigenvalues, then we can see that there is a Poinsot distribution of the eigenvalues. So the separation becomes an exponential distribution. So if we take just a square billiard, and for that square billiard, the eigenvalues will fall like this. They will be like a exponential distribution. Whereas BGS conjecture says that if we consider a quantum system, classical counterpart of which is non-integrable, in that case it follows Wigner-Dyson statistics. That is, for this case, considering the symmetries, there are different kind of distribution. For this case, it is predicted to follow x time exponential minus x, this kind of distribution, and it exactly fits with that. So this is what BGS and Berry-Tabor conjecture is about the energy level statistics of different systems. So the the eigenstate thermalization hypothesis, which says that if we consider long time dynamics, what we can get that the operator at longer times, it becomes the microcanonical answer. It converges with the statistical average. So what we get from the what we previously got from the quasi probability distribution, it is also implied by the random matrix theory and energy level statistics. So, so this is the background that I have discussed. So I have discussed about this Wigner function, Berry-Voros hypothesis, and classical limit, and we saw that from quantum chaos, using this idea, we can get to thermalization. Also, using random matrix theory, quantum chaos also leads to thermalization through this Wigner-Dyson statistics. There is another way to get thermalization. That is the thing is entanglement measures. So by studying entanglement measures, we can also see thermalization. Now I will discuss about that. So before discussing my results, first I want to introduce some basic notations and definition, so then it becomes easier to understand those results. So first thing is realignment. So there are two kind of realignments. One is just exchanging. So realignment means exchanging index of one subsystem with the other. So for example, if we take the index from the first subsystem and from the second subsystem and exchange them, then it becomes R1. And another realignment is exchanging the second subsystem from here and first index from here. So these are the two realignment. So in the matrix form, you can say that you take each block of the matrix and then vectorize them, and that to column wise. For example, if this is your xr1 is just take the elements of the first block column wise. So this one, and make it a column, and then choose this block, do the same thing, and then you continue. Another important operation is partial transpose, which is denoted by T1, T2 or gamma 1, gamma 2. Here we exchange the indices of the same subsistence. For example, we can exchange I and J, or we can exchange alpha with beta. So these are called partial transpose. And here, as you can see, partial transpose, the T1, it is just exchanging the blocks of diagonal. We are just exchanging the off diagonal blocks. Whereas the T2 is just exchange, we take each block and just exchange the off diagonal terms. So this is just basic notation. Now we will define a quantity. We will define some entanglement measure. So one simple entanglement measure is linear entanglement entropy for a bipartite pure state, and this is just simply 1 minus trace of rho a squared, where rho a is the reduced density matrix which we can get from partially tracing over this the total density matrix which we get from the pure state. Now before introducing another entanglement measure, first I want to introduce this isomorphism that any bipartite unitary operator can be mapped to a pure state of 4 qubits. It is valid for any dimension, not only qubits, any dimension. So what we can do,
What
we
is the
can
bipartite pure state? Can you explain again?
so yeah, bipartite pure state means you can just write a wave function for the system. If it is a mixed state, you cannot write in terms of a wave function. So it will be a density matrix.
Okay,
Did you get my?
okay,
You cannot define a particular wave function for the system. In that case, you call it to be mixed state. So yeah, now you can rewrite the bipartite unitary operator. I mean, you can map the bipartite unitary operator to a pure state where you can get the state from this operation. So 5 plus are just the Bell states, maximally entangled states, and you perform this operation. U tens are identity, but the Bell states are acting upon A and C, and another one acting upon B and D, whereas the unitary is acting on A and B. So to diagrammatically, we can represent it like this: that these arcs represent Bell states. So A, there is a Bell state between A and C, and B and D. U acting upon AB, and this vertical lines means just identity operation. So this is what this means. So now the previous entanglement measure, what we saw, this linear entanglement entropy, it was state dependent. But now we will see another entanglement measure which is completely state independent. So we can do that by starting with the Smith decomposition, but not of a vector, of but the Smith decomposition of this of unitary operator U. And utilizing this Smith decomposition, we can define another entanglement measure known as operator entanglement, which also, so these are the this Smith coefficients, these lambdas, and this also can be achieved just by knowing the realignment operation of this unitary. So you just take your dagger, take a square and trace over it, then you can get this. So this is why I introduced it earlier. And one nice thing about this operator entanglement is that for any local operation you will always get this to be 0, and if you choose the swap operation, that is swapping the qubits, that operation maximizes the entanglement for any dimension. Now to understand how what does it mean physically, so you can see here that if we consider the 4 parties A, B, C, D, what I showed before, so and these states represents the entangled state. So there is an Bell state between A and C and B and D. So E of U, this one measures the entanglement entropy along this partition between. I mean, if you take the partition between, I mean, in one partition, if you keep A and C, and another partition B and D, then it measures the entanglement between this partition. Whereas entanglement of operator entanglement of US, it measures. Sorry. The operator entanglement between operator entanglement measures the entanglement entropy between this partition AC and BD. And the operator entanglement of US, it measures the entanglement entropy between this partition AD and BC. Sorry for my mistake previously. So this is what the operation significance of operator entanglement is. Now
How it
also we can,
measures? I mean, you said that it measures the
sorry,
entanglement. I mean, how you are defining that measure? I mean, operator entanglement.
yeah, I showed you the operator entanglement. You can just get, if you know, if you know the Smith decomposition of any operator,
Mm-hmm.
immediately you can write the operator entanglement for this.
Okay.
And also the way we define this four party system, if you look at the reduced density matrices, for example this one, the reduced density matrix for this row AC, it is itself 1 over d squared. Then you are dagger, you are dagger. So now if you use the same analogy as this, let me go back to this linear entanglement entropy. It is just 1 minus trace of rho a squared, right?
Yes.
So if you do the same thing, if you just do 1 minus trace of rho AC squared, because this we already showed that this operator is equivalent to a four party state. I I showed this before that this bipartite unitary is same as, I mean it can be mapped to a pure set of four qubits, right?
Hmm. Yes.
Yeah. So operator entanglement of this U, and which can be mapped to a four qubit state. It is equivalent to an equivalent to entanglement entropy of the state U, not the operator, the vector U. And the entanglement is just 1 minus trace of rho squared, the linear entropy, the linear entanglement entropy. In this case our rho is rho AC. It is our reduced density. I mean we are considering the partition between these. So in one side we have AC. AC is one subsystem. B and D is another subsystem, and this is the partition. So if you
Okay.
just take trace of rho AC squared, it gives this.
Okay.
It- yeah. So similarly, if you consider an operator entanglement of U times swap, you can get in terms of partial transposes. So we can define another entanglement measure, which is called entangling power. It can be defined in terms of only the operator entanglement of U and operator entanglement of swap. So the reason to define it, we will see what is the reason. Yeah. Another definition is you determine the linear entanglement entropy of this U acting upon some random vectors phi 1 phi 2, and they have been chosen from Haar measure, that is a uniform distribution. So Haar measure means, for example, if this each of the vector have only two entries in the simplest scenario, so the numbers will be drawn from a four-dimensional hypersphere. So this is what Haar measure means, and this is how we define entangling power. Now, if you just think of the U4 gates, you can, I mean, heuristically, we can draw some partitions that there are some local gates which can be written as a tensor product. Also, there are some non-local gates, but not all of them are perfect entanglers. Some of them are perfect entanglers. That means they create the maximum entanglement, and there are some which does not create perfect entanglements. I will come to this. What does it mean? So how to differentiate between this U, SU, US, and SUS, these different operators? The entangling power that measure is not sufficient to distinguish between these four. So that's why we will introduce another complementary quantity known as gate typicality. The and if you look at the definition of entangling power, so there is a plus in front of E of US and minus in front of ES. We will just exchange the signs, and there is another factor of half in front of it. So this is what is called gate typicality, but the physical significance of this has not been found yet. So introducing these two quantity, we can project the set of two qubit gates on a 2D plane. This is the entangling power and this is the gate typicality. So swap is swap operation, swapping two qubits. It is definitely a non-local operation, but it does not have any entangling power. So that's why if any local gates and swap, both of them have entangling power to be zero. So this is why we need GTU to distinguish between these two gates. Now we can see that there are some gates which lie on this boundary. That is, those gates are called dual unitaries. And one interesting fact about those gates are that if you perform realignment operation on those gates, they still remain unitary. Another interesting set of gates which lie on this boundary, they are called two dual unitaries. So even if you perform partial transpose on them, they still remain unitary. There is another kind of interesting gates which are called two unitary, that is intersection of T duals and dual unitaries. That is, it is invariant under both. I mean, it remains unitary under both realignment and partial transpose operation. But if we go to higher dimensions, for example, instead of 2q date, we go to 2q trit. We can see that this two unitary is also present. Now, before coming to the main result, one interesting thing about these two qubit gates is we can rewrite these gates in terms of Pauli matrices, and we can reduce the number of parameters using Cartan decomposition. So, for example, in this Cartan decomposition, we the J runs from 1 to 3. So there are three parameters C1, C2, C3. If we get the same plot for different random unitary gates, and if we plot their entangling power, we can see there is a symmetry. I mean, we can see there is a repetition. To get rid of this repetition, we can use the theory of while group. I will not get deep into it, but using the theory of while group, we can reduce this thing to what is called as while chamber. So from this cube, we can get into this tetrahedron, and even the half of the while chamber is sufficient to uh, represent all the gates that I showed, all the two qubit gates. This is we are just parameterizing them. So now I will come to the main part. I will define what is known as Floquet operator. So this Floquet operator U, it is defined as T dagger U tensor L T U tensor L, where T is just a shift operator. It shift if you operate this on a set of qubits, it just shifts the qubits on the right side. And also I am assuming periodic boundary condition. So to picturize it, you can think of this the first line, the first bottom line, it represents this U tensor L, where in this case L is just 6. And this then T dagger U tensor LT, it is just shifting all the unitaries by one qubit. So time is flowing along this vertical direction, and these are the qubits. I mean, these are the qubits. So we can represent this Floquet operator by this. Now, what we would like to see that what is the operator entanglement of this Floquet operator. Okay. To do that, first we will see what is the operator entanglement of this realignment of this Floquet. We can use some mathematical jugglery, and then it boils down to this case that for L equals 2, it is very interesting that the operator of the Floquet is solely determined by the operator entanglement of this single block. Of this single block determines the entanglement of the whole operator, irrespective of the dimensionality. But this is only for L equals 2 qubits. I mean, it can be q dates, but L has to be 2. And if I just plot, this is the numerical values. I plotted the numerical values, and as you can see that it perfectly matches with the prediction. So I have plotted the predicted curve as well. So it is perfectly matching. We can do the same thing. Instead of taking EU and then E of Floquet, we can take the E operator entanglement of US. and also we can see the same thing. Again, it follows the same curve, and it is one-to-one mapping. But if you look at the entangling power, if you compare the entangling power, then there is no one-to-one map between this U and the Floquet operator. So we can't really write the entangling power of Floquet as a function of this EP of U. Nevertheless, also as I mentioned previously, that for L equals 2, it is very simple that the operator entanglement of Floquet comes as a nice function of operator entanglement of just a single block. But what happens when we increase the L? In that case, so this term which also occurred, I showed previously, which also occurred while calculating the operator entanglement. So this can, it doesn't have a good and nice closed form. We cannot straight away write a closed form because we don't know that what happens when we take some tensor product of the blocks, then realign them. After realigning, we don't know whether we can write them as a function of just simply u of R2. Unless we can write, we cannot reduce. I mean, we cannot write the entangling power of the whole Floquet or operator entanglement of the whole Floquet in terms of just a single block. So now to do this, I used a diagrammatic approach, which is known as folded representation. So I will represent UU dagger like this, keeping two blocks one behind the other. So this diagram means UU dagger. So the unitary condition reduces to just this. So this whole thing means UU dagger, but there is no operation between U and U dagger because I am not connecting the hands of these unitary blocks. But when I am putting a blob over it, it means that they are connected and not only connected. Yeah, they are connected. For unitary, they has to reduce to identity. So that's why this we will use this symbol to represent identity operations. So UU dagger is identity. Also U dagger U is identity. So it depends upon that which hands we are connecting. So now we can do this, and instead of just U and U dagger, we can just stack four unitaries like this. Then we define a gate of another color, but it is the same idea. Then we calculate this quantity, the trace of U realignment dagger whole square, and then there is this constant. And yeah, this one comes, this red lines comes because of the realignment, and then this one comes because of the whole square. You are multiplying the unitaries, and then green ones represent tracing over. So ultimately, we can reduce it like this. That this we can we can mark this as this block and this as some square. So this is how it works. So one block means there are arcs which are not rainbow like. I mean they look like just U's. Whereas where we are putting this square, that means there is a rainbow like arcs. For example, you can see here. So this is our notation. So yeah, now if we start with a Floquet operator, let's say where L is 6. Now we will use this representation what I discussed. So we can get the trace of this Floquet, trace of this UR dagger whole square, and it looks like this. Then we can just rotate it and rearrange. So by some tricks, it simply reduces to this. Pictorially, the this trace ultimately reduces to this diagram. Now you using the fact so that where we have blob one or the four hands, it reduces to identity. Again, when we have four squares on four hands, then again it reduces to identity. Using this fact, ultimately what we get that for any even L, we will always get this nice relation. What I got for 2 analytically using this folded representation, we can get it for the generic L, generic even L. So yeah, now I will come to one interesting fact, that is impact of local dynamics. So as we know that local operations does not increase entanglement, does not affect entanglement. But what happens if you interlace the local operation in between two global operations or non-local operations? For example, u and v are if u and v are non-local, and if you choose some random local operation and then measure the entangling power, take a average over some distribution, you will always see that this is not equal to only the entangling power of u and v. And most of the cases, what you will found that you will find that it is greater than this entangling power of just u and v. So this local operation is also increasing the entanglement. So yeah, you can see that if we just time let the unitary operator evolve in time, this u power n means just time evolution. So it just have a billiard like dynamics. But if you just keep keep interlacing this local operators in between u and v. So u power 1 means you are interlacing it only one time, so u then some local operators then u, it is u power 1. If you keep interlacing them in between u's, so ultimately what you will get, that the average, it goes to average the average value goes to the average entangling power of all the random gates. So this is one interesting thing. Now we will see what implications this have. So before that, we can do one thing. I mean, this is the result I derived, that for the shift operator that I introduced earlier. For the shift operator, the operator entanglement turns out to be this, and we also can derive the gate typicality. So one important thing to notice is that operator entanglement of this U, it is greater than this. I mean the Floquet, the operator entanglement of this Floquet, it is greater than the operator entanglement of T. So we can see this numerically or from this thing. It is also implies from here. Now we will see the thermalization of measures. So this thing, what I said, that interlacing the local gates in between the non-local gates, it ultimately saturates to the value where all the where we get the average of all the random unitaries drawn from Haar measure. So this is what we will define as the thermalization, that it is converging with the average of all the random unitaries drawn from Haar measure. So what we can see, that this is the operator entanglement of a particular kind of Floquet, where I chose each of the blocks to be C not gate, controlled not gate. And then if we plot the operator entanglement of this Floquet and this Floquet times swap, we can see that there is a periodicity in this case as we increase the number of steps. But now if I introduce randomness, we can see that it is not periodic at all. For example, so this is the Floquet I discussed in the previous slide. So you just use C naught as each block, you just use C naught. So you can see the periodic green curve, right? But if you just go one step ahead and make it, you put some kind of randomness. For example, instead of choosing all the three blocks to be C naught, I am choosing only the middle block to be C naught, and the left and right are just some tensor of some local unitaries. In that case, you can see it is not periodic anymore. It is saturating to a particular value. And as you keep increasing the order of randomness, for example, this, so here all the UAs were same along space and along time. All of UAs are the same. But now if I make them different, not on yeah different not only along space and also time, because initially they were just C2 C1 C2 D1 D2, but after one time, after the just the shift, they are changing. So I'm changing them along time and also along space. So you can see that because of this higher randomness, it is saturating faster. If I go beyond that, if I choose all of them to be some random unitaries like this, just some random unitary tensor 3. So in that case, I mean, this is 2 qubit unitary obviously. So in this case, you can see that it is saturating faster. And if I go to the extreme case, that I was choose in this case I was choosing the unitaries to be the same spatially and also temporally. But now if I change in both in space and time, you can see that it is going very fast. This blue curve, it is going, it is saturating very fast. So this is what we call as thermalization of measures. So the more we increase the randomness, we can see that they are thermalizing. The entanglement measures are thermalizing. And this is the plot for operant entanglement, then of the Floquet time swap. I mean the evolution of Floquet, then time swap. We can also see that unlike this C naught case, it is not periodic anymore, and they are just very close to the saturation. So we can see the same thing for entangling power instead of operant entanglement. If we just plot the entangling power, so instead of this nice periodic curve, we can see the saturation very fast. It is the same case as I discussed
Uh,
previously.
Niladri, this saturation is due to the maximization of entropy, or we can say something like that, or something
Yeah,
else.
so this operator entanglement is just operator entanglement entropy. I was not mentioning the word entropy. Operator entanglement is kind of entanglement entropy. So the faster it saturates, that means the faster the entropy is increasing. You can
Okay,
say that.
and what is the reason for that? I mean, how you define the corresponding
Yeah,
cause for that saturation?
yeah. So you can see that there is a nice symmetry. In the first case, there is a translation symmetry, right?
Mm-hmm.
So if you remember the blocks, let me get into the previous this thing. So I am choosing this bipartite unitaries to be C naught. All the blocks to be C naught. So you can see that there is a nice translation symmetry along space and along time, right?
Yes.
Because when I will choose the square of this operator, again you will see the same pattern repeating along time, and also all of them to be. If I choose all of them to be C naught, then there is a symmetry along both time and space. But when I'm introducing the randomness, for the example, when I chose the first order of randomness, what I did, so I I chose the middle one. I took only three blocks. I chose the middle one to be C naught, the left one to be some random unitary, and also the right one to be some random unitary, random local unitary. So because of this randomness, we are losing the translation along this, the spatial translation. Did you get my point? And also, if I choose these to be random, I mean this one, this block, and this block to be random, and even this block to be different, and this block to be different. So it is kind of extremely randomized situation. So the more I'm introducing randomness, the more it is breaking, it is losing the symmetries. This is how you can interpret.
Okay. Okay.
Yeah, I will come how we can relate this to a classical system. So we can, not exactly classical, but our, I mean, which can be physically interpretable. So one thing is we will go back to kicked Hamiltonian system. So we specifically kicked Ising model. So this is our kicked Ising model where this delta is again that delta train, and the potential is defined like this. So if you look at the time evolution between two kicks, so it becomes exponential minus IV tau and minus IH not tau. So this whole thing can be compared with this thing what I used in my previous cases. This n one non-local bipartite unitary and tensor of some UA and some local unitaries. So you can compare this, and by the virtue of Cartan decomposition that I introduced earlier, the example I showed you, that C naught, for C naught the Cartan decomposition is just, I mean the parameters, the Cartan parameters is just pi by 400, and it is equivalent to comparing this, that if you define the tau to be pi by 4 and this h indices to be the, I mean if you compare the h indices with the Cartan parameters, they are the exactly same, they are 100. These two are 0, and along x, if you choose one, it exactly maps to C naught. So there is a mapping between the key Ising model and what I showed earlier. I mean, we can take any bipartite unitary, we can get the Cartan parameters. Then if we substitute back to be hx, hy, and hz, we will obviously get a physical system. So this is what it means. So the more you are, so in special case where there is a symmetry, you you get this periodicity, but the more you break the symmetry, you get the thermalization. So this is what it physically means. To summarize the whole picture, so I discussed this. This was our scientific background. Now I started with entanglement measures. Then I discussed about the Floquet. Then one thing we noticed from the Floquet that local operations can impact the entanglement. To be specific, for shift operator, we showed for shift operator. Then from this Floquet operator, we saw that time evolution for defined order of randomness, and then we discussed how integrable to non-integrable we can distinguish between the transition between the different regimes of Ising model, and also the saturation that I mentioned in this time evolution that actually implies thermalization. So this is the summary of my whole presentation. So yeah, if you have any questions.
Okay, first of all, thank you, Niladri, for your excellent presentation. And now the floor is open for questions. If anybody want to ask any questions, they can just unmute yourself and ask it. Any questions? Uh, uh, if not, let me ask one question first of all.
Yeah,
That
sure.
you showed that how from entanglement measures you define the Floquet operators and you
Yeah,
relate
yeah.
to that Ising model to different randomness. Now, if you from this randomness, what kind of systems you want to apply these methods? I mean, physically speaking, what are the realizable systems you want to apply these methods and where
I mean,
it can
you
be
are asking
realized?
me that what can be the other spin models, other.
Yes, yes, yes. Not about not the kick Ising model. Apart from kick Ising model, what are the other
So
realizable
yeah,
system in different
it
fields?
is
Mhm.
it is not a very trivial job to find a physical system, because what I did was I started from completely mathematical point of view. I mean, just for my mathematical curiosity, I studied the Floquet operator, and luckily because of this Cartan decomposition, we can have a mapping between kicked Ising model with our case, but not in every spin model we can connect this thing. But the spin model has to be a kicked model, that's for sure. The model has to be something of this form. Now you have to think of a potential which is physically interpretable.
Okay,
We need to have this form because we have to decouple this v with h naught. I mean, between two kicks the time evolution will be exponential of minus this whole Hamiltonian. For kick Ising model, luckily you can just decouple this. I mean, you can just break into
okay,
two exponentials, and because of this you can compare with this, that
okay.
some bipartite unitary with this local.
So if there are Hamiltonians which are breakable in this fashion, you can map it to the
Hmm. Yes. Yeah. And they have to be kicked for sure.
okay. They have to be kicked Ising model. So I mean, you by kicked you mean that there should be a delta function of that kind.
Delta. There will be a delta train
There will be
and with the
Dirac
potential.
comb or sort of
Yeah,
things.
Dirac comb.
There should be a Dirac comb sort of things. Okay. Uh, so still now there is no physically realizable systems apart from this. You know.
No, I haven't read of any other
Okay. And
system.
what are the future aspects? I mean, what you can do more from this using this model?
So one thing that can be studied, not using the kick Ising model, but from the mathematical construction. So this is what I showed for nth time steps, but only for few dimensionality, and I only use this C naught gate, which actually maximizes the entanglement. If you recall from the 2 qubit plot, let me get into that. Just I'll get into that quickly. That yeah, C naught lies at the maximum for 2 qubits, right? So this I chose this one. So what we can check, we can check fractional powers of C naught, and we can do the same analysis, and we can see how it is changing. I mean, it is we have to check how I mean the saturation is going definitely very nice for this C naught, but what happens with this fractional power of C naught, or whether this is valid only for these special cases. I am not sure. If you just take any random gate instead of this C naught, we can get the same periodicity for this integrable case as I showed. So in that case, the thermalization will be a fuzzy thing, because we had this periodicity. We can claim that okay, this one was integrable, but as we increase randomness, it is not. So we can, if we do this analysis for different gates, we can get some concrete claims, which might be more general than
So have you
this.
studied for any other gate rather than C naught?
No, I haven't studied for any other
Okay,
gates.
okay.
I just did for CNOT.
So for C naught, this should be the randomness. So
Yeah,
you want to claim
and
that for
also
other gates.
also for any random gate, I don't think this one will be valid. I mean,
The
one very
Cartan, the Cartan
Cartan.
decomposition.
So one hard problem is given a gate finding the Cartan parameters.
True. Okay.
So once you are given with Cartan parameters, then you can find that what is the closest physical gate to it. What is the closest physical operation? For example, C naught is just controlled knot.
Hmm.
But given any random Cartan parameters, you cannot find any physical operation. So it is one problem.
Okay.
And the other way around, the problem gets tougher. That given a gate, find the Cartan parameters, because for a unitary, a 2 qubit unitary has uh, 16 parameters, whereas in Cartan you have just 3 parameters because you are throwing out some local unitaries.
Okay.
Yeah.
Yes. Thank you, Niladri. If there is any other question, uh, then again thanks Niladri for your excellent talk.
Uh, I have
Yeah.
I have a basic question.
Yes. Yes.
Yeah. Sure. Go ahead.
So the reason you're taking the CNOT gate, is it just because to get a maximally entangled pair of qubits? Is that the reason why?
Mm, yeah, you can say that maximally. Yeah, that gives the maximal entangling power. Yeah, if you change the entanglement measure, not always C naught will give you the maximum entanglement. For example, if you choose operator entanglement, for operator entanglement, swap increase maximizes the measure. This is one thing. I chose C naught because it that for C naught the Cartan parameters are
And
known from this while group and while chamber. Let me
for
get
the
into that.
first bear talk sessions,
Uh,
so let me stop
the
the
Cartan chamber. Just one second.
recording.
This- Yeah, the Cartan. So if you see that this C naught, for C naught, it is known that it is simply, I mean, it is just matter of some definition of the factors. So it was just pi by 400. So it was a known and known gate. That's why I used C naught. I could have used DC naught. I think the result would be the same,
There should be
because
pi
for
by
C naught
4
and DC
instead
naught,
of pi by 2, or is that correct?
no, it actually depends
Okay,
how you define
okay,
the parameters.
okay.
So you can change any factors. So you can say one reason I chose C naught, because is it has some physical meaning. Firstly, it has a physical meaning. If you compare the other gates, so other available gates, local gates, you can choose any local gates. Swap also has zero entangling power. So either you have to choose double C naught or C naught. Or another one is F4, that is quantum Fourier transform. But this one is very simple, right? Control C naught. This is the reason I chose. You can definitely choose this thing. I mean other gates, other known gates, and you will. I hope you will get the same result. Did I answer your question?
Yes, yes. Thanks.
Okay.
Thank you for that.
Okay, any other questions you have? Okay, if not, then let's thanks Niladri for his excellent talk. Recording has started. Recording has started. Good evening, everyone.